Like this, let's find the ratio of from the previous video. Sigma 1 by sigma 2, therefore, is q1 by 4 pi r1 square by q2 by 4 pi r2 square. So then 4 pi get cancelled. So q1 by q2 into r2 square by r1 square. But you already know that, um, um, we already know that, so they given the potentials are the same. They charge the same potential. Yes, we equated it already, right? And therefore, you already know that q1 by q2 can be replaced as r1 by r2 into r2 square by r1 square. So r1 and r1 get cancelled, r2 and r2. So r2 by r1 is surface charge density of sigma 1 by surface charge density of sigma 1 by sigma 2 will be r2 by r1. You already know that the radius of the is greater first sphere is greater, and so surface charge density of the first sphere will be surface charge density of the second sphere will therefore will be larger. So this is the way. I couldn't complete it in the previous video. There's some glitch in my recording. I don't know why it's like this, so I had to break it and do it again. So I hope you understood. Therefore, since the radius, um, it's like the radius of the first one is bigger, sigma 2 will have a greater surface charge density of the second one will be larger than the surface charge density of the first one. So that completes this question, eighth question, which is continued from the previous video. So let's take the ninth question. uh, um, So the graph has been given, and it's a graph between f and 1 by r, or I don't know, it's potential in 1 by r, I think. It's not very clear. I'm not able to enlarge this once again. It's a graph between, potential and 1 by r, V and 1 by r. They've given this to be like this, and they've given this to be like this. They're talking about this as q1, they're talking about this as q2. And it's a linear graph because V is inversely proportional to R, but it's directly proportional to 1 by R. It's perfect. The question is, um, if the negative potential is negative, which means the charge will be negative. Two graphs shows the variation of electric potential with 1 by R from a point charge for 2 point charges Q1 and Q2. What will be the signs of the two? When the potential is negative, the charge will be negative. So Q2 is negative and Q1 is positive. And which of the two charges has larger magnitude? V's formula itself is 1 by 4 pi epsilon naught into Q by R. So if the potential is larger, the charge will be larger. And from the graph, we infer that Q2 will be greater than Q1 because the potential, even though it's a negative, its magnitude is bigger. So then thus I would write it like this. So let's go to the next question. So the 10th question. Oh, so which of the have to have larger magnitude? Okay. 10th question. Two identical capacitors, 12 picofarad, each connected in series. Two identical capacitors, 12 picofarad, each connected in series across a 50-volt battery. Calculate the electrostatic energy stored in the combination if they would be connected in parallel across the same battery. Find the value of energy stored in this combination. This is series, so it will be 6 picofarad is the equivalent capacitance. And half C V square, 6 into 10 to the power minus 12 into V square is 50 the whole square. And in this case, it is 24 picofarad is the equivalent capacitance. So 12 and 12 picofarad, 24. And so it's half into 24 into 10 to the power minus 12 into 50 the whole square. The ratio of these two means 1 by 2, 1 by 2 get cancelled. 50 square 6 is 6 4 so 24. So therefore it's 1 is to 4 is the ratio. They're asking about the ratio of this. Find the ratio of the energy stored in the combination. So let's go to next question, which is the 11th question. The 12 negative charges of the same magnitude placed equally spaced, okay, minus q, minus q, minus q, like that. 12 charges are placed, which means, 12 charges are placed. The radius is r. Find the electric potential at the center. Electric potential, it's just 1 by 4 pi epsilon naught into minus q by capital R plus 1 by 4 pi epsilon naught to minus q by capital R, and so on. And how many such charges are there? 12 such charges. So it's 1 by 4 pi epsilon naught into minus 12 q by R. I mean, 1 by 4 pi epsilon into minus 12 q by R. Or that will be the net potential at the center. And what is the electric field at the center? You know that the potential at the surface will also be the same as what is inside. So you write like this. But E is equal to dV by dr, and it's equipotential surface, and so therefore the electric field inside will be zero. Since its potential is a constant, the electric field will be zero. So continuing the recording. Am I? Yeah, is it recording now? 13, yes. So let's continue. But then the second part of the question, they are saying that the charges are placed at 120, at an angle of 120 degree. The charges are placed, not equally placed. It's different, okay. It's placed, all the 12 charges are positioned like this. The radius is still r. So if you have to calculate the potential at this point, it will still be the same. The potential will not change. It's 1 by 4 pi epsilon naught into minus 12 q by capital R. It will not change. What about the electric field? Electric field here will not be zero, because it's in the previous case, since there is minus q minus q minus q and all. See, supposing there's plus q plus q plus q, the charges in the electric field inside is zero. Also, we can justify it because they emanate from positive, emanate from positive, emanate from positive. They all cancel out each other. So we can say that the electric field is zero in this case, but this is symmetry. But here we can't say that because there's no symmetry here. So then the electric field, this is minus q. So then there, every time there will be an electric field towards negative charge, and there will be a resultant which is towards that direction. There will be an electric field which will be directed towards somewhere towards the left side. The resultant of all these vectors. So that answers this question. Find the electric potential at the centers unchanged now, and the electric field will not be zero for the second case, because they are unequally placed and there will be a resultant. Okay, so let's go to 12th question. A parallel plate capacitor of capacitance C is charged by a potential of V. The battery is now disconnected and is connected to an uncharged capacitor 2C. This capacitance is C and this charged to potential V. This is 2C, but its uncharged, so potential is 0. Find the ratio of the charges on A and B. They connected, no, after connection. Ratios of the charges. The ratio, the charge will flow from higher potential to lower potential, but they have the given, it's going to be series of parallel. A parallel plate capacitor of capacitance C is charged by a battery. The battery is disconnected and uncharged capacitor B is connected to 2C. The charges tend to flow from a higher potential to lower potential. So then until across A. So they have given that it's across, it's connected across, which means it's like we can say that it's not series, it's parallel. So the equivalent capacitance is 3C, and the common potential V common is therefore C1 V1 plus C2 V2 by C1 plus C2, provided this is also positive and this is also positive and negative. So let's assume it like that. C1 V1 is the initial charge. They already told you that it is charged, C and V are the value, and V2 is 0, so this becomes 0. By C1 plus C2 itself is 3C, and so C and C now get cancelled, so you get V by 3 to be the equivalent, the common potential. Once you know the common potential is V by 3, you can multiply that with the respective capacitance, because Q is equal to C into V, this capacitance into V by 3, and this is a Q top and Q at the bottom will be 2C into V by 3. So then, and therefore you found the charges on both the capacitors. Find the final charges on A and B. It's done. And the The total energy stored in A and B finally. What is the total energy stored? It's half CV square, but C itself is 3C. Into V square is V common, V square by 9. So then 3, okay, this is 3C. So it's 3 and this is 9. So this will get cancelled. So you get 1 by 6 CV square. And this will be the energy stored in the final one. And what is the energy stored in A initially? Initially it will be half CV square. Because charge to that's only energy available. The other one is uncharged. So this is the final energy. Are they asking for ratio? If they ask, you can write it. So the total energy stored in A and B is done. So next question is so then on this sum is over. 1 second, hold on. So let's continue with the 13th question. So if this is C1 and there's a C2 here, there's a C3 here, there's a C4 here, there's a C5 here, and this is B, this is A. You have a, a simple wire which is connecting this and this, a simple wire which connects this and this, which shows that when you take a color pen and draw, you see this, it starts from here, it's connected to a C1, and this C1, from that it goes, I'll do it with a different pen, from C1 it goes to C2, it also goes to C3 and C4. So from C1 it goes to C2, so connect C3 and a C4, and these are parallel, okay. And then from the other end, you come from the other end, you have a C5 which is here, which in turn is connected to a C4 as well as C3 and C2. So therefore these three are parallel. It's a simple wire, so it's always parallel. So then therefore this, or if what is the value that's been given, and that in equivalent capacitance, each of 2 microfarad. This is 2, this is 2 microfarad, this is 2 microfarad. So you just have to add it, you'll get a 6 microfarad. This is a 2 microfarad and this is another 2 microfarad. So they are in series, so then therefore it's 1 by 2 plus 1 by 6 plus 1 by 2 into 3 into 3. So 3 plus 1 plus 3. So it will be 7 by 6. So it will be 6 by 7. Can we say it is 6 by 7? So that is the equivalent capacitance. What are they asking? Is it microfarad? So 10 to the power minus 6 farad or microfarad. What are they? Each of them two capacitance. Find the equivalent capacitance. This is the way to do it. I hope you understood. So let's go to the second subdivision question, where if a DC voltage of 7 volt is connected between A and B, okay, the ends are A and B, how much charge is drawn from the source? So you got the equivalent capacitance, and Q is equal to C equivalent into V, which is 6 by 7 into 10 to the power minus 6 into 7, which is 6 microcoulomb. That is the total charge. And how much charge is drawn from the source, and what is the energy stored in the network? Energy stored is half CV square, which is half into 6 by 7 into 10 to the power minus 6 into V square is 7 square. One of the 7 and 7 get cancelled. 7 6 are 42. 21 microjoule will be the energy stored in the system. So let's go to 14th question. Two parallel plates capacitors such as X and Y are connected, have the same area and separation between same separation, has got air between the plates, while this has got dielectric medium with dielectric constant 4 between them. So first one has got air. Calculate, and this has been connected to a 15-volt battery. Okay, calculate the capacitance of each capacitor. The equivalent capacitance of the combination is 4 microfarad. Okay, you know the capacitance in this case is epsilon naught into A by D. In this case is K into epsilon naught into A by D. Okay, so then they both are in series. So, or you can take it as, so then therefore it's K into epsilon naught into A by D in multiplication C1, C2. by C1 plus C2. What is common here is epsilon naught into A by D into 1 plus K. So then epsilon naught, D and D get cancelled. You get a K square epsilon naught. So what was I doing? C1 C2 by C1 plus C2. Why should there be a K square in C1 C2? So it's only K into epsilon naught square. So you'll get a K by K into epsilon naught into A by D into 1 plus K is all I'm getting. And this is the C equivalent. And they have said that this itself is 4 microfarad, the equivalent capacitance itself. So then uh, calculate the capacitance of each capacitor. Oh, and K it's been given as 4. So substitute that 4 into epsilon naught into A D into 5. So this will be 4 by 5 into epsilon naught into A by D. And epsilon naught into A by D is nothing but the capacitance of the original capacitor, the first capacitor. It's itself is sorry guys. um, Something is wrong with my Samsung tab. So what was I doing? So shit. Okay, so you have a capacitor X and a capacitor Y, and you know this is we found the equivalent capacitance. Yes, we found the equivalent capacitance, and what was it? This was epsilon naught into A by D. This was K into epsilon naught into A by D. Both of them connected in series means it's epsilon naught square A square by D square with a K by epsilon naught into A by D into 1 plus K. So epsilon naught A get cancelled, D gets cancelled. So it's K by 1 plus K into epsilon naught into A by D. And this itself is given to be an equivalent, is given to be a 4 microcoulomb. Yeah, 4 microfarad. Okay, then now this K itself is given to be dielectric medium with dielectric constant K. So it's 4 by 5 of epsilon naught A by D is equal to 4 into 10 to the power minus 6. The 4 and 4 get cancelled. So epsilon naught into A by D itself is 5 into 10 to the power minus 6, which is the capacitance of the first capacitor. So calculate the capacitance of each capacitor. So this will be 4 times. So the second one's capacitance will be multiplied by 4. So dielectric constant is 20 into 10 to the power minus 6. Okay, or 20 microfarad, and this will be 5 microfarad, whatever the answer is. And then calculate the potential difference between X and Y. You know that you got you got the capacitance to be 5 and 20. So then therefore you can, it's a series, so it's 5 into 20 by 5 plus 20, which will be 100 by 25, which will be 4. This you have a 4 microfarad to be the equivalent capacitance, and which has been connected to a 15 volt battery. So since it's connected, and you can find the charge Q is equal to C into V. C is 4 into 10 to the power minus 6 into V is 15. So it's 60 into 10 to the power minus 6, which is 60 microcoulomb is the charge that is flowing through this. Once you know this is a charge which is 60 microcoulomb, 60 microcoulomb, the same charge is going to flow through here. And you know the capacitance of the first capacitor is 5 microfarad, and the next one is 20 microfarad. So once you know the charge and you know the capacitance, you can find the potential. So V is equal to Q by C. So in this case, it will be V is equal to Q by C. For the first case, it will be 60 into 10 to the power minus 6 by 5 into 10 to the power minus 6. So 5 ones are 5, 5 2 are 10, 12, 12 volt. So 15 volts minus 12 volts, this will be 3 volts. So the potential difference will be, therefore, what is it? We got 12 volts, 12 minus 3 will be 9 volts. So that will be the potential difference between these two. I hope if any mistakes that you spot, you're able to identify, you tell me. I'm just randomly doing the sums. Once I get the equivalent capacitance to be 4, multiplying with the voltage to get the charge. Once I get the charge, it's in series. So potential is equal to Q by C. 60 by 5 is 12, so the 3, and the potential difference will be 12 minus 3, so therefore it's 9 volts. Okay, So let's go to next. Estimate the ratios of the electrostatic energy stored. Electrostatic energy stored is half CV square, and that is also half CV square, where you should write half into C is a common equivalent in each one, in X and Y individually. They're asking for each one, so you write half Q square by C here. Half q square, or you know the respective potential, you can do half cv square also. You know the capacitance here. Capacitance is 5 microfarad, so 5 into 10 to the power minus 6. And the potential for that in particular, if you found it to be 12 volts, then no problem, you can substitute that 12 square and find the answer here. Similarly, you can also do half cv square. If you know the respective voltages, you can calculate the respective potential. So then that's about that sum. You can complete that sum. Okay. That's about, and then you have to find the ratio of it. Okay. So let's go to 15th question. 15th question. Capacitor 4 microfarad. A 4 microfarad capacitor is charged by a 12 volt battery. The battery is disconnected. Now you're disconnecting it and you're inserting a dielectric medium of constant K is equal to 8. Okay, is inserted to fill the plates of the capacitor completely. Yeah. So find the change in the charge. So first, what is the initial charge? CV. So 4 into 10 to the power minus 6 into 12. 12 fours are 48 microcoulomb is the charge, because you already charged it to 12 volts. Now this is the initial charge. Now inserting a dielectric, but aren't you disconnecting? It's disconnected. Once it's disconnected, you know from the tabular column, the charge will remain the same, 48 microcoulomb. Only the capacitance will increase by 8 times, that k times the original capacitance. So then what was the original capacitance? 4 microfarad. So 8 into 4 into 10 to the power minus 6 will be 32 microfarad. It just multiplies like that. So what happens to the capacitor? Okay, what happens the potential difference between the plates of the capacitor? So when it is 12 volt, you're disconnecting, that will become V by K. So 12 by 8. So moment to disconnect, the potential drops by K. So then therefore it is 4 3s are 12 and 4 2s are 8. So the potential thus drops to 3 by 2. And then what else you can say? The energy stored. It will become divided by K. Do you know the initial energy? The initial energy is half CV square, which is half into 4 into 10 to the power minus 6 into 144, which is 72. 4 to the 8, some 4s are 28. That has to be divided by K now. Divided by 8. 8 3s are 24. 8 6 are 48 into 10 to the power minus 6. So this will be the final energy, because energy will also be divided by K. So what is next question? Is the 16th question. A 200 microfarad capacitor, a 200 microfarad capacitor having plates separation 5 millimeter is charged to a potential of 100 volt. It remains connected to the source. Using the insulating handle, it's still remaining connected, okay? Using insulated handle, we are just doubling the distance between them, which means you're moving it to 10 millimeter. Distance d is getting increased, and a dielectric constant 10 is introduced between the plates. K is equal to 10 is introduced completely. Explain the reason how the capacitance, electric field between the plates, and energy density of the capacitor will change. Okay, so you are increasing the distance by 10 millimeter. And so the new what is the original capacitance is 200 microfarad, which is epsilon naught into A by D, where D was 5 into 10 to the power minus 3. So now what is the new capacitance? It's K times epsilon naught into A by the new distance is 10 into 10 to the power minus 3 meter. So K itself is 10. You know from the previous equation what is epsilon naught into A, you can cross multiply this. Epsilon naught into A is 200 into 10 to the power minus 6 into 5 into 10 to the power minus 3, which will be 10 to the power 3, right? and it will be 1 micro epsilon 1 10 to the power minus 6 is epsilon naught into A. 10 into 10 to the power minus 6. Again, the system is hanging. But I can say 10 into 10 to the power minus 6 by 10 into 10 to the power minus 3. Do the calculation, you get the new capacitance. So in the question, they had asked for the um, explain with reason how the capacitance changes. You know, you can substitute like this, and that's how the capacitance changes. So just doing a close up. Okay, and I'm continuing to record. I'm just continuing to record. I'm having hell a lot of issues with the Samsung Notes, but still I'm managing to do it for you guys because you have exams. So then, how does the electric field between the plates change? How does the electric energy density between the plates change? So you know that in this it was 5 millimeter, in this it was 10 millimeter, and also dielectric constant of K was inserted. Um, how will the electric field between the plates change? And but still staying connected is what I remember in the question. It's still staying connected to the supply, and we are just widening the distance by insulator handle. So then, therefore, this will the electric field, since it's now still connected. The electric field will not change. It will just be E only. You know that the electric field will not change because um, E is equal to V by D. E is equal to V by D, and okay, so it is still staying connected, right? It is still staying connected. E is equal to V by D. The potential does not change because it's still staying connected. D does not change. So E remains the same. Energy density of the capacitor. What is the energy density of the capacitor? The formula is half into epsilon naught into E square. The energy density's formula is half into how you know half CV square. It's half into epsilon naught into A by D into V square. V can be written as E square D square. D and D get cancelled. A into D is volume. This is energy formula. In energy, bring the volume down. So energy density it becomes half into epsilon naught into E square is energy density. And how does the energy density change? Nothing, because electric field is going to remain the same. So energy density also remains unchanged. Correct? Because there's no change in the electric field or potential, because it's still staying connected only. No? So that is my understanding of it. I hope you can cross check with your teachers for the final answer though, and dispute with me if there's anything wrong. The two capacitors of 10 microfarad and 20 microfarad are kept in series. So you have a 10 microfarad and a 20 microfarad, which are connected in series with a 6-volt battery. After the capacitor fully charged, the slab of dielectric constant K is inserted between the plates of the two capacitors. So after it's fully charged, we are inserting a dielectric constant K after it's fully charged. Which means after it's fully charged, meaning once the capacitor fully charged, there'll be no more current coming from the 6-volt battery. The capacitor once fully charged blocks a DC, blocks a DC. And so then it's fully charged, and so it's like it's can we say it's disconnected therefore? Um, After the capacitor fully charged, the slab is inserted. But the plates, how will the following be affected? The slab is introduced, the electric field. So you all know the answer. But I just want to check that it blocks the DC, but it's still connected. So I have a doubt once again. So do not take it like this. This is not okay. Okay, just it's still not completely disconnected. It's still connected. Though it's fully charged, it's not going to draw any more charge. You can't say it's an open circuit. It's still closed circuit only. Okay. So then the um, electric field. The question is not about electric field. It's about electric field energy. Energy stored. Okay, the question, it's half CV square is the formula, and um, electric field energy increases by K. V is going to anyway remain constant. It's still connected only, no? It's still staying connected. Mm, so the potential is not going to change. The capacitance will change, right? Because it's still connected, it will be K times. So it will be Kc into potential does not change. So then that puts K times the energy will always be K times the original energy. You know that. So electric field energy increases by a factor of K. K times for both the capacitors is going to increase by K times. So second is about they're asking about the charge. Of course, it will increase by K times in both the capacitors by the tabular column. The potential difference between the plates remain the same as it's still connected to a battery of 6 volts. The potential difference is no change. There's actually no change. Whatever was originally the potential difference between the two capacitors will continue to remain the same. So that's the answer you have to write. I hope you're clear. And this is completely from the tabular column that I taught you in the class. So let's go to the next question. Next question is there is a circuit. One second. I'll just draw the circuit for you. So that's sum number 18. So there is this sum number 18. Yeah, let me read the question. You have a battery like this, and you have, sorry, it's connected to parallel to two other capacitors in parallel. Each one is of 6, another is of 6 microfarad, and this is of 12 microfarad. And this one goes to 3 microfarad, and then comes and lands up here. So this is the circuit, and they're asking what is they've given that the 6 microfarad capacitor, there's an electric field is E. The no, the energy stored is E. Energy stored is E. So in this, it will be 2E. Why? Because it's got the same voltage V. Both these capacitors, mm, I hope it's writing. Is it hanging? It's again hanging, guys. So I'll just temporarily hold the recording. I will just switch it off and switch on. So I'm going to temporarily halt the recording. I'll continue in the next video.